Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the University of Helsinki over in Finland, where I study cosmology. So that means that I study the universe, the contents of the universe, how it evolves, how it interacts, basically everything happening inside the universe. It's a great topic. I love talking about the universe. I love talking about cosmology and coming here on YouTube, on Twitter, wherever you're watching from, and chatting to all of you amazing people about the cool and amazing things happening in the universe. I was just delayed slightly. We had a very minor technical issue right before clicking the go live button, but we sorted it out and we're here. So, today's topic is particle cosmology. We're going to look at how we can bring together particle physics, the physics of the tiny, and cosmology, the physics of the universe. It's a fun topic. Before we get into it, just a reminder to everyone, if you're watching on YouTube, if you haven't done so already, please click the subscribe button, leave a comment, like the video. It's how I build the audience. Just help me build the thing up. You know how YouTube works. Just press all the usual buttons. My hair is ridiculously bright. It got bleached in Vienna. I was in the sun for way too long. And yeah, this is apparently what happens when I go in the sun. This is why I don't go in the sun. This and because I actually burn in the sun. But anyway, particle cosmology, the topic of today. And this is a big topic, and I'm not going to be able to cover it all by myself. So I have a special guest today, and I'm going to bring Jasmine on screen. Coming on screen now. Hello, Jasmine. Welcome to Cup of Cosmology.
Yeah, thank you for having me.
Do you want to introduce yourself to the audience?
Yeah, so I'm Jasmine. I have a background in theoretical physics, specifically particle physics, as you might imagine from the topic. But I've studied mostly electroweak phase transition things, which if you're a regular viewer of the show, you might know about. And if not, don't worry, we'll cover it later.
Yeah, so great to have you here. Really nice. And let me just say hello to David and Scott and the regulars coming in. It's great to see you, and to anyone new who's watching, welcome. Regular or new, you're all welcome here. If you've seen the show before, I'm sure you'll learn something new today. If not, stick around and see what it's all about. So yeah, you just mentioned electroweak phase transition and a few things like that. So before we jump into that, you are almost a PhD student, right?
Yep, I start in September with Venus Cruise at Dias.
Exciting times. Are you looking forward to starting your PhD?
It is terrifying and very exciting.
Yeah, that's pretty much the standard feeling. Terrifying and very exciting. So, we want to talk today about particle physics and cosmology and how everything fits together. And as always, this is an interactive stream, so you people can ask any questions you want. Feel free to ask away. If you're watching over on Twitter, you should find a link to join the YouTube stream directly in a comment reply to the first tweet. So feel free to come over to the YouTube channel where you can actually join the conversation as well. Unfortunately, Twitter doesn't let you join the conversation just yet. So you threw out a big word here of electroweak phase transition. So I want to go back to that. But before I do, I just want to get your impressions of why we should think about particle physics and cosmology together. Because particle physics is the study of the early universe, cosmology is the study. Sorry, particle physics is the tiny particles in the universe, cosmology is the cosmos. Why do these things actually fit together? How do these two things fit together?
Well, as you slightly misspoke there, the beginning of the universe is a very small place, only constituted of these fundamental particles. There's no structure yet, and it's too high energy for any even atoms to form yet. And so it makes for a very interesting place to study particle physics because we can access energy scales that we can't get at the LHC or even its iterations on the LHC. And then all of that just leads into what we see today, the structure, the galaxies, the CMB, all that good stuff.
Yeah, so if we think about the history of the universe, and I will just bring an image up on screen, which you've all seen many times, but it's a great image. This is just a standard history of the universe, going from the Big Bang on the left, early universe, up until today on the right. I love this image. There's a few timescales written here. But basically, we're considering a system that is almost 14 billion years old. And the further back in time you go, the smaller the universe was, because the universe is expanding, and the higher energies we had. So if we can go back to these very high energies, we're basically at the stage of the early universe. This is why particle colliders like the Large Hadron Collider try to reach higher and higher energies to push us back to this time. So in this early universe, in the first few seconds, or even the first few minutes after the Big Bang, the forces that dominated were the same ones that dominate particle physics today. So the early universe is really the playground where we expect particle physics and cosmology to overlap. And I see we've got some fans and regulars in here as well, people who know us both. It's great to see everyone in the comments. Hello, and thank you for being here. So we were just saying the universe, particle physics, but there was a big thing you threw out earlier of electro-weak phase transition, and that is a big topic that we have spoken about a bit on this show. But let's assume that nobody here knows what electro-weak phase transition is. Yeah, and as David is saying, please do like the stream if you haven't done already, leave a comment, subscribe, just usual YouTube things. So, what is electroweak phase transition? I guess we could start there with what do we mean by electroweak and what do we mean by phase transition? Maybe we can split those concepts first. So, what do we mean by electroweak?
So I guess electroweak is the joining of the electromagnetic and the weak force, much like how, well, historically the electric force and the magnetic force were considered separate, and when Maxwell came along, he realized that you could put these in the same mathematical framework and unify them. As it turns out, you can do the same thing with the electromagnetic field and what we would call the weak force, the force that dominates radiation processes, proton decay, things like that. And so in the early universe, when you have these high energy scales, you have this unification between the electromagnetic and the weak force.
Yeah, and this is important because we know there are four forces in the universe. So the electromagnetic one, the weak, as Jasmine just explained. Then we have the strong nuclear force, which glues things together. And we have gravity, which makes things drop down and is surprisingly the force we understand the least, but we pretend we know everything about gravity. So we believe that in the early universe, all four of these forces were united. And if we ever figure out how that works, we would have what we call the theory of everything. We're not quite sure how gravity fits with the other three. We're still trying to figure out exactly how the strong, the weak, and the electromagnetic fitted together, but we know that at some point in the very early universe, the electromagnetic force and the weak forces were united in what we call electroweak. So at some point, instead of four forces, we had three. We had gravity, we had the strong force, and we had the electroweak force. And then we mentioned phase transitions. So phase transitions is something that in the first 6 years of this show we didn't talk about, but in the last year I have talked about it substantially because I now work on phase transitions. Apparently, somehow I've ended up in phase transitions, which is a cool topic. So, in your words, Jasmine, what are phase transitions?
So I guess starting first with a phase, I guess a phase is just sort of a smoothly behaving set of matter with respect to temperature. So water is a phase, and then you heat it up enough, and suddenly it stops acting smooth. It becomes steam. It rapidly expands and lowers in density, and this sort of non-smoothness is where you get a transition.
Yeah, so I remember we had someone on the show a few months back who's working on phase transitions, and she was explaining it with ice sheets on the water. And I got very sidetracked because that weekend I'd walked on the frozen sea in Finland, which is still mind-blowing to me, to the point that 8 months later I'm still thinking about this. But yes, you can use water as a way to imagine these phase transitions where you go from solid, liquid, gas. So we have a question here. Let's see the question from James. I understand how matter is converted to energy, but unsure how to understand how energy is converted to matter. So this is indeed relevant for the early universe, but then we have the question here, basically, how do you get particles? How do you go from energy to matter? This is a question that we don't really know how to answer. Do you want to take a stab at that, Jasmine? It's not a question we actually have a real answer to.
I guess we can see that energy in the form of photons can make a matter and antimatter pair, and that's something that's relatively well understood. And then recently, what Hawking radiation was discovered. So usually when this matter antimatter pair are created, it's quite unstable and will do what matter and antimatter do and collide and make more energy, annihilate. But you can get situations where they can separate far enough that they can no longer annihilate, and you do get the the more permanent creation of mass. But how we get a universe from nothing is an ongoing question.
And it is also a very relevant question for today, because this is something where particle physics and cosmology really have to come together to figure out, how we get to this. And maybe we can just come back to that later, because there is a word for this, like creation of matter. We can come back to that. But we were just Hawking radiation is theoretical. We have not found any experimental proof of it, to my knowledge. It is something that theoretically could exist, but we haven't yet found any direct evidence of it. Unfortunately, it would be really cool if we do. But yeah, we were talking about electroweak and phase transition, so now we can put them together. What is the electroweak phase transition?
So yeah, we have this idea of unification of the electromagnetic and the weak, and much like when you cool steam down, it becomes water. When you cool an electroweak system, it becomes an electromagnetic and a weak system separately. The symmetry between the two are broken.
Yeah, so it's when we went from having 3 forces to having 4 forces. So when the electromagnetic force and the weak force separates, this produces a phase transition. And this is what we call the electroweak phase transition in the early universe. And this is something that took place in the first picosecond of the universe, so billionth of a second of the universe. And this is something that has dramatically influenced the rest of the universe. So this is one of the ideal places where we can talk about particle cosmology. So you mentioned that you work on electroweak and things like that. Can you explain a bit how this electroweak phase transition actually relates to what you do, to what you work on?
Yeah, so I guess as a theorist, you're always trying to push the understanding of what we know, and at the moment, that is the standard model of particle physics, which can explain a lot of what we can see at the Large Hadron Collider, but can't explain everything. Has quite a few holes, especially when you factor in cosmological data. The biggest one that I'm interested in is the fact that the standard model can't explain why there's more matter than antimatter. And it was hoped in, I think, around the 80s, 70s maybe, that this could be explained with the electroweak phase transition, that something about this phase transition would mean that you can produce more matter than antimatter. And unfortunately, the Higgs that we measured later at Atlas was too heavy to let this happen. And so my work is looking at, well, how can we add things to the standard model that get us this extra matter over antimatter?
Yeah, so there's a lot of really cool concepts to unpack here. And we're going back to the question that James asked of how do we create matter. So as Jasmine was just saying, we know that we have matter and not antimatter. But in the early universe, it should have been created in equal quantity. So the question of why is there matter and not, just energy? Why didn't everything annihilate? Is a very, very valid question that we're trying to figure out. So, just recapping what Jasmine said here, we thought that this could actually be explained via the electroweak phase transition, but then we measured the Higgs boson at the Large Hadron Collider, and we measured its mass. And based on the mass of the Higgs boson, we know that the electroweak phase transition probably cannot really explain this lack of symmetry between matter and antimatter. But of course, if we're going to throw this out, we now have to explain what is the Higgs boson. So do you want to take that? What is the Higgs boson? Hey, Georgia, great to see you. Haven't seen you here for a while. Great, really nice to see Georgia. If anyone doesn't follow Georgia, make sure you do. Georgia does an amazing wildlife show all about bats and human and wildlife. It's amazing. Sorry, go ahead. What is the Higgs boson?
The Higgs boson is the particle we would associate with the Higgs field, which doesn't really answer the question. So to go on to the Higgs field, I guess it's much like any field. It permeates all of space-time. So at every point in space in your room, there is an amount of Higgsness in it, and then the Higgs boson is what mediates that field. Much like how the photon mediates the electromagnetic force.
Yeah, I always like to think of the Higgs field and the Higgs boson as the person at the party who's handing out cake to everyone, because the Higgs field and the Higgs particle is what gives everything else mass. So you can imagine there's this Higgs field, as Jasmine was just saying, it's something that is everywhere in the room. There's a certain amount of Higgsness here with us. It's like that question: is the Higgs here in the room with you today? Yes, it is. It's everywhere. And this Higgs field basically makes everything else move slower. So things trying to move through the universe are suddenly in this Higgs field, and this slows them down, and this is equivalent to them gaining mass. So because of the Higgs field, everything else gains mass. And now we have to put it all together. So how is the Higgs boson or the Higgs field related to the electroweak phase transition? This is a tough question to answer.
Yeah. So the Higgs field, when you look at how it behaves at high energies, it looks like a U shape. So it looks like this, and so the Higgs boson is just happily sitting in the middle of this U. And then as the system cools, because the universe is ultimately expanding, and so the energy density is getting lower, it starts looking more like a W. So it goes like this. And the Higgs boson, being very lazy, wants to be in this lower well. But the problem is that there's a barrier between the two, and so the Higgs has to overcome this barrier through quantum tunneling or thermal fluctuations, which I'm not looking forward to having to explain. And then once it tunnels through this barrier, we get the phase transition. Suddenly we have this, as I sort of said before, this non-smoothness in behavior, where suddenly things have mass, suddenly things are moving slower.
So we can basically say that the turning on of the Higgs is what in part produces the electroweak phase transition. There's a bit of a chicken and an egg problem there of whether the phase transition produces a Higgs or the Higgs produces a phase transition. Correct me if I'm wrong. But I always see them as like these things happen together.
Yeah, I think these things happen together.
Yeah, I guess then we have to ask the question of linguistically, which came first. But get off on a tangent there. So you threw out the word quantum tunneling. So briefly, and we're not going to go into quantum tunneling because we could do a whole stream about that. The idea is if you have imagine you have a very small mountain and something's down here and wants to get to the other side. Now you could have a tiny fluctuation of energy that will push it over. But particles can do this fun thing where they just walk through walls occasionally. This cannot happen often. But if you have a Higgs bashing against this potential an infinite amount of times, at some point there's a very small probability that it passes through. And this is what we call quantum tunneling. So where you just go down. And if anyone remembers my streams about the vacuum death of the universe and the expanding bubble of death, we can go back to the idea of quantum tunneling and Higgs and stuff like that, because that's a super fun topic and really, really fun. I remember Kylie Hill saying that if not for quantum tunneling, our sun couldn't exist because it's not hot enough to allow nuclear fusion. I have heard that as well. That is also a fun thing, that we need quantum tunneling for the sun to actually work. But that's also something that I will not go into detail now. If you want to, Jasmine, we can, but I would just skip past that as that's a nice anecdote.
That is a nice thing to know, and I don't want to touch it with a 10-foot pole.
Exactly. That is a very nice thing that you can go listen to Kyle Hill talk about. So we've covered electroweak phase transition, Higgs, how it all fits together. So now maybe we can bring it back to what your work is, now that we've introduced all of the concepts. So we said that we have this lack of symmetry between matter and antimatter. We have the electroweak phase transition and the Higgs boson turning on and giving everything mass. And you said what you're trying to do is understand how this could potentially be related, right?
Yeah, so we know that if you just have the standard model Higgs boson, it can't produce more matter than antimatter. But what you can do is you can start adding more Higgs that will have different masses that can give it the extra physics it needs to produce more of this matter over antimatter.
Yeah, so this is what we call like beyond the standard model, because we know the standard model isn't enough. So now we're going beyond the standard model electroweak phase transition. Unusual question, we love unusual questions here. Is the study of particles specific to cosmology? Are other fields of science using particle study? I love this question, James. It's a great question. Usually when you talk about particle physics, the people who study particle physics are particle physicists. There's a whole field of physics for particles. You can have experimental particle physics, you can have theoretical particle physics, which are people making these predictions of how you go from like this phase transition to Higgs to things like this. You can have a lot of different types of particle physics. And then you can really branch out. There's a discipline of astrophysics called astral particle physics, which is let's take the particles from the cosmos and play with them. Now, I've often called myself a particle cosmologist because my work is sometimes at the interplay between particle physics and cosmology. But then you also have other things like nuclear physics or atomic physics, which is the study of atoms and how it all fits together. And that is also very connected to particle physics. It's not at all an unusual question. Particles are definitely not only the realm of cosmology. And in fact, often you will find in the same institute particle physicists and cosmologists. And it is extremely important that we talk to each other because we learn a lot about what everyone else is working on. So, just want
quickly add to that. A lot of the methods used in particle physics, like your quantum field theory, would show up in, I think, condensed state matter physics. A lot of your sort of modeling things as fields there.
Yeah, so particle physics appears in a lot of places, not just in cosmology. And yeah, let's not get into metaphysics, shall we? So you talked about what you're going to work on in your PhD. So just to bring it back a bit, did you do similar work during your masters? Did you work on something else? What did you do during your masters? Because it was also particle cosmology.
It was also particle cosmology, yeah. I worked with Mark Hindmarsh, who's been mentioned before, on well, but very much the same topic, really, but more from the is it theoretically possible for this to even happen? Can we construct models that allow this to happen? Whether these models are useful or can happen is another question that someone else can answer. I'm just curious as to whether the mathematics lets this happen, and that's what I did in my master's project.
Which is very fun because your master's project was with someone who is now my co-supervisor and a colleague of mine. Small world.
Yeah, siblings of physics.
Yeah, academic siblings. It's always fun. Yeah, it's always nice to find people. I was at a conference last week and I was meeting up with a bunch of people who shared supervisors and were like, you're my half academic sibling. You're my academic sibling. You must be my academic cousin, trying to figure out how the trees work. But yeah, it's always a fun thing to do in academia. So we talked about electron phase transition, Higgs, and all of these fun things. And baryogenesis, we didn't give the word before, but baryogenesis is exactly this topic of how do we get matter from energy. So we talked about a lot of things already, but the field of particle cosmology is very broad. There's a lot of things we can cover here. And one of the places where particle physics and cosmology really come together is something that everyone on the show we've seen before has heard me talk about, dark matter. So we know that the universe has three components: everything we see, everything we're accustomed to, everything that we see, like we're used to interacting with, everything from the coffee to me, we're normal matter. And normal matter only accounts for 5% of the energy of the observable universe. Then there's 25% in the form of dark matter, which is this weird type of matter that is invisible. It doesn't interact with light in any way, but it does interact by the gravitational force. And then the remaining 70%, 69%, 70% is dark energy, which is this weird type of energy that is pushing the universe outwards, and that's everything we know about dark energy. But dark matter, we have no idea what dark matter is. And it could be particles. It could also be primordial black holes. Now, we're pretty sure it's not space dragons, but that's about as far as we can go with dark matter. We can rule out things. But it's reasonable to think if we have our 17 building blocks of the standard model of particle physics, which gives rise to normal matter, then there could be a complex part of the dark sector as well, where we have a dark standard model that produces a dark matter. And the cool thing is, because dark matter interacts by the gravitational force, we can measure its effects on cosmological observables. So we can understand things about dark matter by looking at galaxies, how galaxies move, how galaxies distort light, how stars move about in galaxies. All of this tells us about dark matter. Also, how structures are clustered together in the universe's cosmic web. And of course, the biggest piece of evidence we have for dark matter is the CMB, the Cosmic Microwave Background Radiation. We lasted a whole 25 minutes before I brought it on screen today. So the CMB is the oldest light we have in the universe. It's the background radiation in any direction we look, and it tells us a lot about dark matter. So dark matter really is the place where cosmology and particle physics need to talk to each other. And I think you wanted to mention a few things about dark matter as well, right? Or
Yeah,
feel free to jump on.
So I guess the first thing and most important thing, the idea of space dragons being dark matter, I don't think would work because they would breathe fire and we would see it as light.
That's why we know it's not space dragons. Everything
Okay.
else is fair game.
Okay. So yeah, I guess dark matter from a particle physics perspective is very interesting because, as I mentioned before, there are lots of problems with the standard model, and when you start introducing fixes for those by adding new particles, as we do, we're very unimaginative in that regard. They can be dark matter candidates, which requires a few interesting things. They have to somehow come into existence and stay in existence long enough. They can't be moving too fast or be clustered in the wrong way, have the right density, and it means that you can actually, hopefully, constrain new models of physics with our understanding of dark matter, which is part of what I want to do.
It is fun. I think dark matter is really a good place where we can really bring together particle physics and cosmology. And I also do like that, you can put 100 people who work on dark matter in a room and everyone will approach it from a different perspective. In fact, 2 weeks ago, time is weird, 3 weeks ago at some point, in July, I went to 2 conferences. It's been an exhausting few weeks. I'm still recovering from that. But one of the conferences was dark matter. And there were people there thinking about dark matter from angles I had never even considered. And there were there were particle physicists, astro people, cosmology. It was a great conference. And we basically left with the idea of, well, we still don't know what dark matter is. The conference is called Identifying Dark Matter, and then the concluding talk was like, well, I guess we should go start doing this thing of identifying dark matter. We're trying, but it's difficult. And I just want to make a comment because people are saying that I took 25 minutes to bring up the CMB, and I'm not sure if my comment actually sent to YouTube. The CMB is now in the Cup of Cosmology official logo, which appears on screen at the start of every stream. So technically, the CMB is now appearing in the first second. So anytime I bring it up, it's already been shown in the first seconds. Space dragons could breathe neutrinos. I love that thought. I really love that thought, and that will allow us to talk about neutrinos if we want to. But dark matter. You said you want to work a bit on dark matter. What type of things do you want to do with dark matter? Because as I was just saying, we can come about it from hundreds of different angles. So what do you think you would like to do with dark matter from a cosmology perspective? Obviously, identify it.
Yeah. So, as I mentioned, as part of the sort of fixing of this baryogenesis, the production of more matter than antimatter, the method that I'll be exploring that with is adding extra Higgs particles, and these extra Higgs particles can be dark matter, and I've not started yet, so I might be saying things that are wrong, but I think my idea is that if we have an idea of how much dark matter there is in the universe, say 1 dark matter particle per cubic meter, which I'd imagine is very off as a dark matter density, but if your model starts producing 10 or 100 dark matter particles per 100 cubic meter, then it's very likely wrong. You're producing too much dark matter to be physically viable. And so you can then rule that model out without doing any of the potentially more computationally or just more difficult tasks. You can do the easy bit and then move on.
Yeah, so it's very cool when you think about all the things you can do with dark matter. And apart from understanding dark matter for its own sake, we can also, try to use dark matter to solve other problems that we have with our standard picture of the universe. As Jasmine was just saying, we can try to use dark matter to help understand why there's more matter than antimatter in the universe. So really understanding dark matter is not just let's understand it because it's 25% of the universe, but also, so I keep laughing at the comments here because there's a couple of inside discussions going on there. But yeah, I was ill last weekend. That's why we had to postpone the stream. That was completely on me. I got a bug, but I tested negative for COVID like 5 times, different over the space of having symptoms. And I tested negative like 2 days ago again. So it wasn't COVID. I just picked up some other bug because there are other bugs going around. But yeah, it wasn't COVID in the end, fortunately. But yeah, some people talking about gravitational waves in the CMB. But yeah, we can use dark matter apart from just like let's learn about dark matter. We can also use it to try to understand some of the other things in the universe that are slightly puzzling to us, like why there is more matter than antimatter in the universe. Now, what I've always done with dark matter is ask the question of how can we actually use cosmology to try to understand things about dark matter. Then we do things like look at the CMB, the cosmic microwave background radiation, my first love in the universe, as everyone knows, and ask questions like, what can dark matter do and still not mess up the CMB, the cosmic microwave background radiation? So can dark matter, for example, bump into things? Is perhaps dark matter not as invisible as we think it is? And usually the answer is no, anything you do to dark matter would mess up the CMB. But that's basically what I've been doing throughout my PhD of my first postdoc and still somewhat. But now I shifted into phase transitions and gravitational waves, which are super fun topics and still let me work on the bridge between particle physics and cosmology, which is fun. So we had this comment just now about space dragons breathing neutrinos, which of course we do not endorse the idea that there are space dragons. So just making that clear, I don't want to see a headline tomorrow of scientists say space dragons are a thing. Just making it clear, we're not endorsing space dragons here, although they would be very cool.
I will endorse space dragons if people want to give me money for that.
Yeah, if people want to pay us to work on space dragons, by all means, please do so. But yeah, there is a great question from David. I was about to jump into neutrinos. I wanted to use the space dragons to jump into neutrinos, as you do. But there's a question about anti-dark matter. So we know that there is matter and antimatter. We were talking about this before. Jasmine was saying how we end up with more matter than antimatter, and we don't know why. So does dark matter have an antiparticle? I'll leave that one for you. What do you think?
So it depends exactly what kind of model you're looking at, but I think it's generally accepted that dark matter could annihilate with itself, or well, I guess there's also dark matter. If it is a particle, does it need to be one particle? It could be many, in some sort of hidden part of the standard model that we don't yet know about. So it could be a collection of electrons and anti-electrons, or well, not anti-electrons and electrons because they're already in the standard model, but equivalently. Also, they can't be charged, but beside the point.
They could be charged under a dark force.
Yes.
So there are some ideas that dark matter could be its own antiparticle, and there are some ideas that dark matter could have other antiparticles. First, it would be very useful if dark matter is its own antiparticle, because then we can hope if dark matter and anti-dark matter, or dark antimatter, I guess, one of those. Anti-dark matter sounds better to me. But if dark matter and anti-dark matter crash into each other, annihilate, they could produce, hypothetically, they could produce standard model particles. So one of the ways we try to find dark matter is by looking for extra particles that we don't expect. For an example, if we consider antiprotons, there are a few things in the universe that produce antiprotons, like pulsars, which are just rapidly spinning stars. So if we could estimate like how many antiprotons we expect to see at any given time in our galaxy, and then we measure how many antiprotons there are, and if we get a few more than we expected, we could say there's something else producing antiprotons, and this could be dark matter and anti-dark matter bumping into each other. And in fact, we have done exactly this. We have measured antiprotons, and we have found that there are too many antiprotons. And now, of course, the debate is trying to figure out if these antiprotons are dark matter, or if these antiprotons are actually coming from something else in the galaxy, like a population of pulsars that we just don't understand properly. So that is a nice idea to think about, that if dark matter can annihilate with anti-dark matter, it would help us find it. So there's a few ifs here. If it can annihilate, and if this annihilation produces something we can actually measure, because it could be that dark matter and anti-dark matter annihilate and produce a dark particle that we also won't see, which doesn't help us much.
I guess along this line as well, my understanding is about 10% of Higgs decays aren't understood where they go. We don't know what we would call the branching ratio. It's this sort of undefined, and that's primarily because Higgs physics is very hard to do. It's quite noisy. but it could be that it's producing dark matter.
Yeah. So you threw out the word branching ratios there, which is something we use often. So maybe we can clarify, what is a branching ratio? What do you mean when you say a branching ratio?
So I guess like a branch on a tree, it's the amount that branch takes up of the total tree. In that sense, it's a ratio. So if you have um, a top quark decaying, you would have it decaying into a bottom quark, say, and other things, or maybe a strange quark, and each one of these would have their own associated probability that you could compare with each other and get a branching ratio.
Yeah, so when we talk about branching ratios, I think that's a very nice explanation using the trees there. So it's just how likely is a particle to decay along specific directions? And the Higgs decay, we know more or less what it should decay into, but sometimes it decays into things that are not along our branches. So it's like there's a hidden branch that we haven't yet figured out. And that's what we mean here when we throw out the word branching ratio. And as always, if anything we say is not clear, please do ask us and we will jump on the question. We're always happy to clarify, explain things again. I think we often forget just how much jargon we use sometimes and how many words we use every day. And then sometimes we suddenly realize, like, wait, this is not a normal word. I notice that with my family sometimes, where I just use a word like, "Oh yeah, I just interacted with him yesterday." And it's like people don't say interact. You spoke to him. That's what normal people say. So sometimes we forget that we use words. We just use them so often that we forget that they're jargon words. So yes, please do tell us if we're using random words that don't make sense, or if something we say makes no sense. Please do ask us. And there was a very nice question again by James a while ago that I want to go back to. Is quantum physics the same as particle physics? Is one a subfield of the other? How do they fit together? So, what do you think? How would you explain quantum physics? Obviously, we don't need to explain quantum physics. Just what is quantum physics?
I guess quantum physics simply is the idea that things are fuzzy when they get very small. You can't exactly measure the position and momentum of a particle. That's, Schrodinger's uncertainty principle is quite well known. And since this applies to the very small things, this is immediately the realm of particle physics. And so we use quantum mechanics, and it's more advanced, I guess, sibling quantum field theory to study particle physics. But I can't think of a way of doing particle physics, I guess, without doing very simplistic particle physics that are like ball bearings hitting each other. I don't think you could get away with doing particle physics without including some quantum mechanics.
Yeah, you kind of do need quantum physics to explain how these particles behave. So, of course, if you're coming at it from a cosmologist, it's just like we have some particle, we just treat it as a fluid everywhere in the universe, then you don't care so much. But if you want to do particle physics, you do need quantum physics or quantum field theory, which is a very fun and difficult concept. And I don't believe anyone has ever understood quantum field theory. I just have the idea that nobody understands quantum field theory.
Yeah, I suppose it's kind of like quantum mechanics ultimately decides how a football moves on a football field. However, you wouldn't use quantum mechanics to describe that because that would be incredibly difficult and not worth anyone's time when you can just use Newtonian mechanics.
Yeah. So I wouldn't describe quantum physics or particle physics as a subfield as each other, but rather quantum physics helps us understand particle physics, and you can do some things in particle physics without quantum physics, but not many. So I would say quantum physics is the toolbox we use to try to understand the particles, if that makes sense, hopefully. But I think it's a great question and a great thing to ask of how we fit particle physics with everything else. We have a question here, I believe, from someone from our Discord server. Of when you say we don't know 10% of the branching ratios, do you mean we don't theoretically know, or was there a mismatch from experimental to theoretical models?
I suppose when you talk about do we theoretically know it, it would again depend on the model, but I would imagine it's the case that we can't pass out 10% of it from the noise. It's not something I really should have looked into more prior to the stream, but I'm just vibing at the moment and hoping for the best. If you are in the Discord server, I can bring it up again later.
Yeah, and if not, feel free to ask again. We can always answer again here in the chat. But yeah, I was just thinking that 10% is vaguely somewhere on my mind, but I also wouldn't answer that question. I don't touch Higgs. Higgs is someone else's playfield.
Yeah.
Everything I know about quantum mechanics I learned from Ant-Man. I would suggest very much not taking any quantum mechanics information from Ant-Man, because that film is about as scientifically accurate as things like don't go there. It's not a scientifically accurate film. It's also not a very good film, to be honest.
It shows string theories. It's not correct. I'll make a bold claim there.
Yeah, let's upset any string theorists. I think string theory is very fun. It just doesn't apply to our universe. Never apologize for the questions you ask. We are always happy to have any questions. There are no bad questions. There are no stupid questions. You never need to apologize for your questions. It's great questions. If it's something we don't know, now we get the fun of going to look it up at home. So never apologize for your questions on this show. This is a space to ask anything you want. But yeah, let's not start a string theory argument here. I did have a holography expert on recently, and I asked the question, does holography apply to our universe? And it does, and I love that. So that's really cool. So some time ago, we wanted to talk about neutrinos and space dragons. Well, not space dragons. We were using space dragons to get to neutrinos. Is there any scientifically accurate presentation of quantum physics I guess you mean in movies or TV shows? None that come to mind currently. Do you know of any that portray it well?
I'm not a big movie person, but I don't think so. Actually, I'm thinking of there is a book. I forget the name of it that portrays special relativity very well.
Yeah.
Like there's it's a world where the speed of light is much lower, and so when you start riding your bike down the road, things start contracting, and you get all these interesting things that we'd only ever see at the LHC, but now you see it in your everyday world.
Yeah, I think there's a few good references for special relativity or general relativity. Like Interstellar did a pretty good job with time dilation and stuff like that. They lost the plot with the whole bookcase part, but otherwise it was fairly accurate. But I'm not, off the top of my head, I can't think of a film that accurately, or a TV series that accurately talks about quantum physics. Also, they do things like, we're going to take a quantum leap. It's like, a quantum leap is a tiny, tiny, tiny thing. Stop using it to mean big leaps forward. Anyway, sorry, pet peeve, needed to rant about that.
I did make a mistake in a quantum mechanics homework where I thought that you could quantum leap 4 meters and not the actual answer, which was considerably smaller than that.
Yeah. That happens sometimes. I remember taking a physics exam, like classical mechanics exam, and I was supposed to be calculating the speed at which a snail was traveling, and we had things like friction and all the stuff to consider. And my end result was that the snail was traveling at something like 10 meters a second, which is ridiculously fast for a snail. And I wrote in my exam, like, this snail either has a turbo pack attached to it, or I've made a mistake in my calculations, but I cannot find it, so this is your problem now. So, yeah. Your dad was a quantum chemist and complained about inaccurate representation. Yeah. Yes, sci-fi, well, as you know, Georgia, we did the whole stream together about sci-fi and what we do and don't like. And there are some things that are good in sci-fi, and there are some things that are bad. And, we love it anyway. Through the good and the bad, we love sci-fi anyway. So, you were going to say, Jasmine?
I was just going to say, I think maybe the importance of science in literature isn't to be accurate, but to get people interested to get into it themselves, and then they can learn that it was all wrong.
Exactly. Yeah, I think sci-fi it's not its job to explain science to us. And I do like sci-fi shows that don't even bother. Like Doctor Who, it never even bothers trying to explain things. It's just like, it's timey-wimey. We're not even going to go there. And then you get other shows like Stargate, which I love, and I'm just rewatching Stargate and finding all the things that bothered me about it, but it's a lovely show. But then they start trying to explain it with wormholes and event horizons, and then they get the science wrong. It's like, you could have just not bothered, just thrown out a random magic word and I would have believed it. But when they try to use actual science and then get it wrong, that bothers me slightly. Like, just do timey-wimey. I'll be happy with timey-wimey. Kyle Hill did a video where he spoke to an expert and said that the time travel in Endgame was accurate according to quantum theory. Yeah. Endgame goes into the multiverse, and we're not going to go there. We're not going to follow Endgame into the multiverse. It just gets complicated when you start discussing things. So we keep getting distracted, and I keep trying to go back to the topic of neutrinos, and I feel like this is now becoming a joke where every time I mention neutrinos, someone is going to change the topic on me. But it's fun. We love taking, we take the conversation wherever you want to take it. Neutrinos. So I want to talk about neutrinos because I love neutrinos. So neutrinos are one of the tiniest particles that we know of in the standard model of particle physics. And they are so small that for a long time we actually thought they didn't have mass. But we know that if they didn't have mass, they would have traveled at the speed of light. We have been able to measure that neutrinos do actually have a very tiny mass. And the way we've measured this is a really cool quantum physics thing, that the neutrinos have three possible flavors, kind of like three flavors of ice cream. And the neutrinos can actually change between these flavors. So imagine if you buy a strawberry ice cream in the shop and by the time you get home it's chocolate ice cream. This is something that neutrinos can do, which is fun. And the way they are linked together means that if they can change flavor, they have to have mass. You cannot explain this changing of flavor if the neutrinos don't have mass. This changing of flavor is what we call neutrino oscillations, and I'm just dumping a whole course of neutrino physics here. So neutrinos, close enough, yes. So in order to explain this neutrino oscillation, so this changing of the flavor, neutrinos have to have mass. And the fact that neutrinos have mass is extremely cool, because if you change the amount of mass that neutrinos have, you would change how galaxies look. So the thing here is that neutrinos are moving through the universe, and if neutrinos have a lot of mass, they're going to slow down. And if they slow down, they're going to clump together more with dark matter, which means they're going to change the way that you can form structures. On the other hand, if neutrinos are lighter, they travel faster and they kind of wash out any structures. So, by looking at the amount of galaxies we have in the night sky and how these galaxies fit together, we can try to ask the question of how heavy are neutrinos? What's the mass of neutrinos? Which is really fun because we're basically trying to get the mass of the tiniest particles we know by looking at a bunch of galaxies and asking the galaxies, hey, how massive are neutrinos? And the cool thing is we can actually do this, which is kind of impressive. I think neutrinos is also a place where particle physics and cosmology have to come together, because neutrinos affect the entire history of the universe, and neutrinos are a particle that we know exists in the standard model of particle physics. Do you want to add anything about neutrinos? Because I can talk about neutrinos for days, and I just want to catch up with the comments here.
Yeah, I guess I will beat you to it and answer James's question.
Go ahead.
That each neutrino would have a different mass. That's something we do know. We don't know which mass necessarily goes with which, but we know that they have different masses. Yeah, so neutrinos. Well, I guess interestingly, we know that neutrinos have mass from the sun. That's when that was first discovered. We saw about a third of what we expected to see from our solar models, and it was an interesting time. Not that I was there, but an interesting time where it wasn't clear whether the particle physics was wrong or the sun model was wrong. But yeah, neutrinos show up as well as a dark matter candidate. The standard model ones have been, I think, largely ruled out as dark matter candidates now.
Completely.
But there are one of the things that we don't know in the standard model is how neutrinos get their mass, and mechanisms to do that can produce new neutrinos that can be dark matter. So again, just another link between the sort of trying to get your particle physics to work and then trying to get your cosmology to work are one and the same.
Yeah. Sometimes you dissolve one field to go to the other, and vice versa. And I'm very amused at Georgia calling neutrinos nutrients, and they do have flavor. So there were also two comments I wanted to make based on what you said there. And one of them is going back to whether neutrinos can or cannot be dark matter. And the reason we know, so neutrinos cannot be all of the dark matter. And we don't think they're a good dark matter candidate. And the reason being, if neutrinos were all of the dark matter, we'd have too many neutrinos. And we can get an idea of how many neutrinos there are in the universe based on things like the sizes of galaxies and based on the CMB and things like that. And if we were to change the amount of neutrinos we have in the universe, we could produce all of the dark matter, but then we would mess up the CMB and we would mess up a bunch of other things. So basically, neutrinos move too fast to be able to account for all of the dark matter. So neutrinos could be a subcomponent of the dark matter, but they can't be all of it. Which then means, they're basically not going to be the dark matter that we're looking for until we don't consider them to be a dark matter particle. And now there is a very difficult question that I feel like we should answer, and I'm not sure if either of us is going to want to answer this. We talked earlier that the Higgs boson gives everything mass. And you just said that we don't know how neutrinos acquire mass. So why can't we use the standard idea of Higgs giving things mass? Why can't we use that with neutrinos? And this is a very difficult question, so no pressure to answer.
It does feel like quite a bit of pressure, though, doesn't it?
No pressure, really, no pressure.
My understanding is that you can't get the couplings to work. You have to do things that we would consider unnatural or unphysical to get such a low mass with the Higgs boson. I think that the lowest that we can do is the electron, although that might have other things going on there that I don't know about. Yeah.
So it is a very difficult question to answer, and this is the type of question you set on a particle physics exam. So I'm sorry for throwing that question at you, but neutrinos have the cool thing that they're all left-handed. Particles come in left-handed and right-handed, and neutrinos for some reason are all left-handed, and this just means it can talk to the Higgs field as well as anything else. There's a lot of ideas as to how we can give neutrino masses, but we have no idea. And this is also something that we're going to need a lot of input from a lot of places. But yeah, that was a super tough question I threw at you, and you gave a very good answer, so well done. Yeah. Sorry for that super tough question. I was thinking, do I want to ask this? Another very good question from James here. Acting smart, you are smart, James, so no worries there. If a neutrino transforms from a higher mass flavor to a lower mass flavor, should an energy be emitted? Where does the mass go? Excellent question. Now, we need to we need to think that there's two different things here. There are the three flavor states and there are the three mass states. So we have three different flavors for neutrinos and we have three potential masses. There could even be two, they could be the same mass, but we have three different mass states and three different flavor states. And they don't perfectly overlap. So there is some mixing between them, but they don't overlap. Which means you can't say the electron or flavor one of the neutrinos, which we call the electron neutrino, has this mass, and the tau neutrino has this mass, because there is some mixing between the masses and the flavor. So it's not a one-to-one correspondence. That we know that their mass is going to change slightly, but it's not going to be that, I changed from vanilla to strawberry, so I'm emitting mass. There is a mixing going on here. This oscillation between one flavor and the other does use some energy, but it doesn't produce mass or lose energy in a way that we would notice. So it's just the thing that we need to distinguish here between the three mass states and the three flavor states and how these fit together. That is a complicated thing to talk about, but there's not a one-to-one correspondence. So what we try to do is figure out the three mass states. And we have some lower limits from particle physics. We have some upper limits, both from particle physics and cosmology. We know that one of them needs to be heavier than the other, and the other one needs to be a bit heavier. So we know the kind of difference between the masses, but we don't know the ordering. So we don't know if there's like two light neutrinos and one heavy one, or two heavy ones and one light one, or three of the same mass. So we don't know the ordering of the neutrino masses. And this is something that cosmology probably cannot answer. There are some ideas, but it is something that is very difficult to answer. So it's very cool. Jasmine, I think you wanted to talk about CP violation.
I did in a minute. I've lost my train of thought on the masses.
Yeah, mass is complicated. Fun topic. So comment from David here. I suppose neutrinos are a form of the dark matter, but not all of the dark matter exactly. They could be a type of dark matter, but we usually don't consider them to be dark matter anymore because they would be a subdominant component anyway.
I think I just remembered what it was, or at least a thought that I had.
Go ahead.
Neutrinos couldn't emit light because they're electrically neutral.
Yes.
But because they do have mass, they could just start moving faster or slower. But that would maybe violate conservation momentum. So I think you could still change mass and energy over in a neutrino without emitting a photon. Not something I'm fully aware of, though.
Yeah, Yeah, that is an interesting point. So, do you want to cycle back to CP violation? Because you just told me you wanted to talk about that. And we do only have 5 minutes left. So,
Yeah.
let's keep CP violation short.
Okay, so
If we want to go there.
the biggest, I guess, thing with neutrinos at the moment is seeing whether a neutrino behaves differently to an antineutrino if they're the same particle altogether. And if they do behave differently, then in the early universe we can actually get this more production of matter than antimatter as well. So it's just another competing method to explain baryogenesis.
Which is also, I just had something else pop up on my screen and had to move it away. So, yeah, we can once again tie neutrinos into baryogenesis, which was the production of matter and antimatter. So, just to say what we mean by CP violation here, this is the charge conjugation parity symmetry. So we know that things should be charge and parity symmetric. If they're not, we say that they violate charge parity conjugation, which is a technical term which takes a lot more than 5 minutes to explain. But we can tie it back to the production of matter and antimatter in the universe, which means we can once again tie everything together. So we have neutrinos, we have dark matter, we have the Higgs, we have electron phase transition. All of this kind of lies at the interplay between particle physics and cosmology, and we really do need both in order to understand these things. And this is why it's also important to have conferences where we bring people together from different perspectives, or have places where we can chat with people from other disciplines, because then we can figure out how to study these things. So in the last 3 minutes of the show, is there anything else that connects particle physics and cosmology? Oh, loud bike. Is there anything else that you would briefly want to talk about how we can connect these things together? Thank you for joining us, Scott, as always. It's always great to see you here.
I suppose I should probably just mention that this is not an exhaustive list. There are plenty of other things in particle physics that can't be explained, and in cosmology, dark energy is the ever-present horror that cannot be explained.
The elephant in the room that we pretend is not there.
Yeah, no, the 70% of the room.
It's just not there. We can't see it. It's just dark energy.
I don't feel it pushing on me. It's fine.
Yeah, we're too small to care about dark energy. Dark energy becomes more important when you look at the whole universe. On small things like the Earth, we don't need to worry about dark energy.
Mm-hmm.
Yeah, I mean, we could also throw out there inflation, which is this exponential expansion in the early universe, which can be explained with different particle physics models. So basically, anytime you try to go to the very early universe, you're going to run into particle cosmology. Because if you're trying to explain something in the universe that started in the early universe, then you go to the energies where individual particles and how they interact with things becomes dominant. So at this point, you do need particle cosmology. And it's always fun to see how these things come together. I've done papers with particle physicists. I put out a paper last year that for me was the most particle physics paper I'd ever done. And for the other 3 authors on the paper, it was the most cosmology paper they'd ever done. And it was somewhere in between. There was a bit of cosmology, a bit of particle physics. I still think it had more particle physics than cosmology, but it was somewhere in between. It was fun because I was referring to that as my particle physics paper, and they were referring to that as my cosmology paper. It was always fun to see how we come about these things. Okay, so before we wrap up, is there anything else you would like to talk about, physics or non-physics? Anything else you want to throw out?
I suppose I should probably plug the server that was been casually mentioned.
Go ahead.
I run a community of trans physicists. You can find us on Twitter, would probably be the easiest place. I think it says @transphysics. You can certainly Google it to find it, and I can put it in the YouTube chat afterwards.
Yeah, it's a great server for trans and NB physicists, and it's a nice place where we have a great community, and it's where we met and then figured out that we actually have like a co-supervisor in common and fun things like that.
Mm-hmm.
Okay, so we're already at the 1 hour mark, so thank you very much for joining, Jasmine. This has been great fun. We've covered some really, really cool topics. I hope you enjoyed chatting to everyone here in the room as well. We have one last question for you from David. Where are you working?
Right this second, my living room. When I start my PhD more broadly, I'll be living in Dublin, hopefully.
Nice. And then I have the perfect excuse to come back to Dublin.
Yeah, no, we can. I'm sure we can fudge
We'll make that happen.
Yeah.
We'll make that happen, yeah. Okay, so thank you everyone for the questions, for the comments. It's been great fun to have everyone here. A few brief announcements. Today is indeed Saturday. I know most of you expect me on a Sunday. We had to reschedule to Saturday this week. This means I will not be online tomorrow. Don't expect me tomorrow. I'm not going to do 2 streams back to back, so no stream tomorrow. Then next weekend, we'll be back to regular schedule. Sunday, 7 p.m. Central European Summertime. So on Sunday the 14th, I currently have no idea what we'll be talking about. I have a week to figure it out. If anyone has topic proposals, let me know. So this Saturday is just an outlier. Next weekend, we'll be back to Sunday. Then the weekend after, of the 21st of August, I should have a guest on who I'm super excited about. And I'm not going to give anything away, but just stay tuned on the 21st. I will announce that in time.
Is it me again?
It is not you again, unfortunately, but it is someone who works on topics that you would be interested in as well.
Okay.
I'm not going to give anything else away. And if anyone hasn't yet seen it, check out the awesome banner that I have on YouTube now. The usual Cup of Cosmology artist, Ania Heber, designed the banner for me. Again, there are a lot of hidden elements and there are a few Easter eggs. So get hunting, tell me everything you can find in the banner. There's quite a few things hidden there. So, thank you everyone for joining. If you haven't done so already, click the subscribe button. It does really help build the community here. Good luck for your PhD, Jasmine, from someone who recently finished a PhD. So, thank you everyone for joining. Thank you, Jasmine. And I hope to see you all again next Sunday, same time as today. And in the meantime, I hope everyone stays safe and take care of each other.
All right, bye-bye.